tails would be an event. And probability is the measuring of the likelihood of that event happening. Right? Play a game. Flip a coin. If I get heads or tails, I win. Yes. Right? Certain 100% of the time I would win in that game. Right? Flip a coin. What would I have to do to lose? I don't know what. We have heads, tails, and legs. If you get legs, I win. There's no legs on a coin, so obviously chances of that would be impossible. That would be 0. And a 50% would be an even chance, and sometimes that's referred to as a fair chance. So if we're playing a game and you win with tails and I win with heads, right? It's a fair game. We both have an equal chance of winning. So sometimes we have a sample. So a sample space is the set of all possible outcomes of an experiment. And then within that sample space, we have a specific event A. So for example, in this class, so my sample space or my population would be people in this class. If I picked someone at random, what are the chances I pick someone with long hair? Okay, so event A would be long hair. The whole square would represent this class. So we have 4, 10, 16 people here today. So my sample space would have 16 people, and people with long hair, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 16 have long hair. What's the definition of long hair? Gets a whole nother problem, but we won't get into that right now. List the sample space of flipping a coin. Well, what are all the possible things? Just a matter of saying heads and tails. Got a little bit trickier when we did the sample space of flipping it twice, right? Because then we had heads, 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 tails, tails, heads, and tails, tails. And if you know this sample space, you can figure out probability easily. How many are tails? 1 out of the 2. How many are heads? 1 out of 2. 6-sided die. 1, 2, 3, 4, 5, 6. Those are all the possibilities when rolling a die. Lots of games like Monopoly. Has anyone ever played Monopoly? Yes. Are you playing, oh, it's McDonald's Monopoly right now. Is there any big McDonald's Monopoly people in here that go crazy? Yes, you collect all the stickers and never win. Oh, so much fun. Right. But every once in a while, you win like a muffin. It's so exciting. Okay. If you toss 2 6-sided dice, what does the sample space look like? Well, you could start listing them. Like you could get a 1 and a 1, a 1 and a 2, a 1 and 3, a 1 and 4, a 1 and 5, 1 and 6, 1 and 7, 1 and 8. No. Can't go that high. Up to 1 and a 6. So the best way to put this together would be to sort of create a chart. I'm going to color code it here very nicely and quickly. Does it make sense that there's 36 possibilities? So every time you roll a dice in Monopoly, you're going to get one of those 36 different possibilities. But some of them happen more often than others. What game has like 7, 11, or doubles? I don't know. I'm trying to remember. Can you see that 7 happens the most times? 12 and 2 are really rare because they only happen once. Does it make sense that the 11 happens twice because you could roll a 5 and a 6 or a 6 and a 5? But usually when you roll the dice, you don't know if you've rolled a 5 or a 6 or a 6 and a 5 because usually you use like 2 white dice or 2 that look the same. But if you played the game and decided you lost one of your white dice and you happen to find another red dice, now you have a red one and a white one, then you'd start to see, oh, I could get an 11 with a red 5 and a white 6, or a white 5 and a red 6. Wonderful. Wow. I don't know what I accidentally hit as a button, but there we go. Oh, other board games. A board game that I see these numbers show up probably, well, not the most, but most interestingly. Has anyone ever played the board game called Settlers of Catan? Yes? Okay. And yes? So in the game Settlers of Catan, they have a bunch of numbers on different commodities, and if you roll that number, so you roll a 6, and a 6 happens to be on wood, then the person who has that place gets a wood card. Next time, for those of you that have played it, next time, look under the number 6, and the number 6 has 5 dots under it. And it has 5 dots to tell the players that it's more likely to happen than the number 5, which only has 4 dots. Those dots are, out of the 36 possibilities, 6 happens 5 times. 5 happens 4 times. Under the 2, there's only 1 dot because it only happens once. If you haven't played that game, you should find someone who has it and play that game because it is very, very fun. Now, theoretical probability is what should happen. How often should I get heads? 50% of the time. And to figure out the theoretical probability, you just find out how many outcomes of that happen divided by the total that you have. So for example, in our chart from before, what's the probability I get a 7? Technically, there are 6 out of the 36 in the chart that we did before that are 7s. That fraction reduces to 1 out of 6. So your chances of getting a 7 are 16%. I'm going to show you a game that I invented. Tell me if you would play or not. Okay? The game is pretty expensive to play. You have to pay $50 to play the game. I roll the dice, and whatever number I roll, you get your $50 back plus what I roll. So if Ian says, yeah, I'll play. Oh, this is bad. I didn't want to give that. Except for the 7. 7 is the only time that you don't get your money back. So Ian says he wants to play, and I rolled a 10. He would get his $50 back plus $10. Right? How often do you win? Right? It's a 16% chance that you lose, 16.67. So you're going to win 83, not quite 83%. Well, a little bit more than 83%. 83% of the time people are going to win. So your chances of winning are pretty good. You want to play? you'd win $5, right? This game is very addictive because you win, you win, you win, you win, you win, but sometimes you lose, and when you lose big. So we had winner, winner, $9. Whoops. Oh yeah, we should add up. We're up 19, 24. You win $3. You win $8. You win $8. Alexis wins $6. Natalie wins $9. So you're watching this. Would you take a chance once and play it? Right? And especially since watching it, what did we, this is not, we had like 8 wins in a row. And Julia's a loser. So she would lose 50. And then we play again and again and again. So this game, on average, I should make, theoretically, 83 cents every time I roll. But it doesn't happen that you pay me 83 cents. It just, if we played it 100 times, I would probably be up $83. But after 100 times, there would be lots of wins on your part. And because your chances of winning are so great, it'd be very tempting to play it, right? Just once. 12. You would have won $12. Then you have to be like, no, stop. Just one more time. Oh, now you have to play because you just lost $50 and keep playing it, keep playing, keep playing. I should really just go to Vegas and open up a booth and quit teaching and win money that way. Here is our new notes package, and I think you're right here. Okay. $20-sided dice. Do I have a 20-sided dice? No, I have a 30-sided dice, which, for the importance of saying things correctly, oh no, I might have lost the paper. I believe it's called a rhombic tetrahedron. I might be wrong. 30-sided object. I mean, it comes up every day in conversation. That's why you need to know these things. So you have a 20-sided dice. You roll it, and event A is defined as it being a multiple of 4. What is the probability of that? Well, a multiple of 4 would be like 4, 8, 12, 16, and 20. Whoops. So does it make sense that your chances of getting that, there's 5 events out of 20 in total, would be 1 out of 4. So if you did this 100 times, we start to talk about an expected value. How many times would you expect to roll a multiple of 4? Well, if the probability is 1 out of 4, you rolled it 100 times, does it make sense that you would expect to get 25 of them? Just like if you decided to guess on a multiple choice test that had 100 questions, and each question had A, B, C, and D. So your chances of guessing it right would be 1 out of 4. Does it make sense that you would expect to get 25% on that test? But not guaranteed. In fact, if I gave you 100 questions right now where you had to guess on every single one of them, it'd actually be pretty hard to get exactly 25%, even though it's the most expected amount. But it would be very hard to pass that test. And those are some of the fun things that we're going to get to in this class. We're going to find out exactly what are the chances of getting perfectly 25. And how many people would get, like, what are the chances someone scores between, in that case, 20% and 30%? Somewhere in that range. We'll be able to figure out those probabilities. So our probabilities will get really quite complicated in what we're going to be able to figure out. Because right now, that question that I just posed to you, your brain should go, I have no idea how I would even begin to figure that out. Now, there's experimental probability. Experimental probability is results based on an actual experiment. Oh, I have a story for you. A coin is fair because it's 50-50. A thumbtack is not. If I drop a thumbtack, it could land pointy end up. Don't sit down when they're like that. Probably don't recommend sitting down, even if it lands on its side. Those are the two possibilities, pointy end up or on its side. But is it 50-50? Or does one happen more than the other? And how would you figure out for a thumbtack? Well, you could do an experiment. We could see, is it close to 50-50? First time, on its side. Crap, I'm going to step on this later. Now it's upright. On its side. On its side. Upright. Upright. Oh, maybe it is 50-50. Mathematically, though, if you do an experiment long enough, it should get closer and closer and closer to the theoretical probability. Now, true story, a professor at the University of Manitoba once applied for a grant and received money to determine the probability of pointed up or pointed on its side. Okay? Of course, when a professor gets money to do this, the professor would like results, but they're not going to flip the tack themselves. They hire a student. Okay? You're going to get, this is a number of years ago, so whatever minimum wage back then was probably like $7 an hour. And all you do, hour after hour after hour, is flip tacks and count them and write the results down. I don't even know what the probability officially is, but I do know that having that job caused mental health damage to that student. If you spent even an hour doing that, what do you think you thought about when you went to bed that night? Just flipping tacks all day? So the student ended up, I think, having some sort of mental breakdown as a result of that job. So don't go home and say, oh, I'm really curious what the theoretical probability of flipping tacks is. I'm just going to do that for the next 16 hours. No, not worth it. So the experimental probability is basically you did it X amount of times, and this is how many you got. Flipping a coin once, hey, I got tails, is not a good experiment to extrapolate to say, this coin is fixed. It always gets tails. I did an experiment. I flipped it once, I got tails. Therefore, it always gets tails. Right? Only a small amount wouldn't likely be the theoretical probability. But if you did it many, many times, then you could figure out something. Okay? The ratio above is called the relative frequency. You can use the relative frequency as an estimate. So the bigger that we do, the closer that we get. Oh, you can play around with your graphing calculator. Let's see. Sit under. Some of the newer calculators, even some of the older ones, if you hit the apps button and something happens, I think there's a probability simulator on it. They're alphabetical. There it is. Probability simulator. What would you like to do? There's no flipping tacks. But you could toss coins. Let's toss some coins. Number 1. Oh. Let's toss it. Oh, I think I have to actually hit this one for toss. There it goes. I got a heads. But you don't have to click it. It says, would you like to toss it 50 times? So I could click this button, and it like, oh, I've gotten more tails than I've got heads so far. Is it about half and half? Well, this, I could do another 50 more. Oh, I have to hit this button. There we go. It's closer to 50-50. How about 50 more? How about 50 more? 50 more, 50 more, 50 more, 50 more. We just tossed the coin in that amount of time 1,901 times. It looks like we have gotten slightly more tails than heads, but it's pretty close to 50-50. Oh, I can't have to hit these buttons. So confusing with the buttons there. Let's escape again. Yes, let's go. Let's roll some die. Okay, let's see what's set. Ooh. How many should we roll? 3, because we haven't done that yet. I have to go over 3 dice at a time. 6-sided. Score table, yes, yes. Okay, let's do this. Let's do this. Yes. Can you see that if you roll 3 die, the smallest number you could possibly get is a 3? And the largest you could get is 18. You know that rolling 2 die, the most typical one is 7. Right? We saw that was the most typical. Rolling 3 die, what number would be the most typical? I don't know. Let's roll. Oh, I want not a 2. I want to hit this button. I got a 1, a 6, and a 5. I got a 12. Should we roll 50 more? Ooh, looks like 11 is the most likely so far. Or a 12. Now, if we actually did this and wrote things down, this would take us a long time to do this with 3 die. It looks like 11 seems to be the most likely. And the more I do it, the more this will appear to be more like what actually happens. Right now, I actually think 10 is more likely than 9. Okay? But is 9 still above 10? But as I do it over and over and over again, without going crazy, you see how 10 is catching up on 9? Oh, 9 is still. Whew. We've now rolled the dice, all 3 of them, 4,901 times. Each time it was completely random. This last time we got an 11. What are the chances of that? The one that happens the most?
Students at this time are so like to acknowledge this date, October 4th. Surgeon Hex acknowledges that October 4th is a day Indigenous women are 3 times more likely to be victims of violent crime than other women in Canada. The National Inquiry into Missing and Murdered Indigenous Women and Girls issued 231 calls to action into justice in a final report in 2019. Sturgeon Heights affirms the value and dignity of Indigenous girls and two-spirited people in our schools and in our larger community. We commit to building a safer society for everyone, and at this time we'd like to have a moment of silence to honor and remember Indigenous women, girls, and two-spirited people who have been murdered or have gone missing. Thank you, and now we'll have our moment of silence. Thanks, everyone.
So if you did the experiment, does it make sense that the experiment says 7 out of 10 times? But in reality, your brain would tell you it should have been 5 out of 10 times. That would be more likely. These are actual numbers. One morning, I stood at the window, and I spent 2 hours until 138 cars went by, and I wrote these numbers down. Do you believe that? No. Of course I wouldn't do that. That would be like, I can make up these numbers. That would be way better than actually sitting there. But let's say you decided to do that, right? Okay. What is the probability that the next car that passes the school is red? Well, based on your experiment says 45 out of the 138 have been red, right? So your chances of a red car passing by the school next is 15 out of 46. I mean, technically, you could sit there and do this data and get lots of stuff and figure out the probabilities and then bet your friends, okay, at 10, we'll pick a time, and then the next car that passes the crosswalk at that time, these are the, and then you could collect the, I shouldn't be all these bet collecting things. There's like, this is not, going to be, you guys are going to all be IB gamblers after we do this. So if the next morning there was 350 cars that pass the school gates, estimate the number of red cards that morning. Well, if your percentage is about 33%, 33% or 15 on 46 of 350 would tell you approximately you would expect 114 of them to be red. So probability is figuring out things, and sometimes our probability is we're using it to estimate what we think is going to happen. Some probability misnomers. Flipping a coin is 50% of the time. If I flip heads 2 times in a row, what are my chances on the next time that I get heads? Should it be less than 50% because I've already got 2 heads? No. It still stays 50%. But a lot of people will think that the past events affect something. And this is like a common superstition. Like you'll hear people say, oh, it can't happen again. But it's still 50%.